From our perspective on Earth, the night sky feels like a permanent fixture, a quiet, unchanging backdrop. But we are actually witnessing a fleeting, highly energetic phase of a cosmos that is constantly in motion. 1 billion years from today, that illusion of stability breaks. Our sun is growing hotter and brighter, increasing its thermal output by about 1 degree every 100 million years. This gradual heating eventually shatters the carbon cycle, killing off the planet's vegetation. As the temperature climbs to 47 degrees Celsius, the oceans evaporate entirely, turning our blue marble into a dry, lifeless rock. Migrating to Mars or the outer moons offers no permanent safety. As the sun continues to expand, its heat will eventually push the habitable zone completely out of our solar system, making every local planet unlivable. Because biological life cannot survive these temperatures, the long-term future of our species depends on our ability to move beyond our home star and populate the wider galaxy. 10 billion years into the future, the sun exhausts the hydrogen in its core. After a final expansion into a red giant, it sheds its outer layers and collapses into a white dwarf, a cold, Earth-sized remnant of a dead star. While our star decays, the entire local group of galaxies is being pulled together. Our neighbor, Andromeda, is currently hurtling toward the Milky Way at 400 million kilometers per hour. Over millions of years, gravitational forces will violently merge these two structures into a single new entity, Milkomeda. The process will likely eject our solar system far from the new galactic core, or out of the galaxy entirely. This move from one star system to another is a recurring necessity. Our universe is burning through a finite, non-renewable supply of hydrogen, and eventually the fuel for all stars will run out. We are currently living in the Stelliferous Sphera, the age of light and creation. But 100 trillion years from now, that era comes to a definitive close. This chart tracks the volume of interstellar hydrogen gas over cosmic time. Eventually, the universe exhausts its raw materials, and the rate of star formation flatlines to absolute zero. No new stars will ever be born again. The lights of the universe begin to fail one by one. Red dwarfs and brown dwarfs, the longest-lived stars, slowly cool and blink out, leaving behind a sky of fading embers. By 10 quintillion years, we enter the degenerate era. The cosmos has become a graveyard of dead remnants, white dwarfs, neutron stars, and black holes. This is a permanent, irreversible downgrade in the state of the universe. We have moved from a time of active energy and light into an age of slow, cold decay. 10 decillion years into the future, even the dead matter left behind begins to fail. Scientists theorize a process called proton decay, where the fundamental building blocks of molecules begin to disintegrate. As protons disintegrate, the last physical remnants of the stars quietly dissolve. Without these building blocks, matter cannot hold itself together, and the universe's remaining structures vanish into a void. This leads to the black hole era at 10 duodecillion years. In this dark epoch, only massive gravitational singularities remain, acting as the final scavengers of the universe's stray energy. But even black holes are not immortal. Through Hawking radiation, black holes slowly leak subatomic particles. As shown here, when particles appear at the event horizon, one may escape while the other falls in. This continuous leakage causes black holes to lose mass over trillions of years. Eventually, even the most massive singularities will evaporate entirely. This proves that gravity and matter are temporary. Given enough time, the laws of thermodynamics will dismantle everything that currently exists. 1 googol years into the future, a 1 followed by 100 zeros, the final black hole in the universe evaporates. This is the dark era. The universe is now a cold, quiet void, containing nothing but a few isolated subatomic particles spread across unimaginable distances. Dark energy continues to stretch the fabric of space, pushing these remaining particles infinitely far apart. They will never interact or form another structure again. This terminal state is known as the Big Freeze. All energy has been evenly distributed, and the temperature of the entire universe hovers just above absolute zero. At this point, the cosmos has reached maximum entropy. There is no longer any usable energy to sustain biological life or power any form of physical machine. If the physical universe is guaranteed to run out of fuel, the only way for a civilization to survive is to find a way out of the system entirely. This survival strategy would have to begin long before the lights go out. It would require transitioning away from biological bodies and into forms that require far less energy, such as digital consciousness or pure energy. By mastering the laws of physics, while energy sources like black hole rotation are still harvestable, a civilization could theoretically progress to a Type 7 level of technology. At this height of technological evolution, an advanced intellect might manipulate space-time itself to construct a new, energy-rich universe in a laboratory setting. In this view, the cooling of our universe becomes a deadline. To survive the Big Freeze, life must eventually learn to outgrow the physical constraints of the reality that birthed it.